Okay. Can everybody hear me? Microphone? Is it not? Yeah, I have to be really close. I feel like I'm spitting into it though. So we were presented with the daunting task of putting together the entire workshop. Although there were challenges large, like sorting through all of the different slides, and then small ones like getting Kirsten's computer the proper electrical supply. As you can see, we were blind men looking for an elephant, and it was confusing at first because we did think it might have been a snake or something. So to give a little context, we're going to look at what the pilot cruise sort of was doing. There was a pilot cruise, it measured some stuff, and that happened at the onset of the monsoon, which was really great timing. So put that into context, the group I was part of, we were charged with looking at reanalysis products to put the spatial large-scale context of the cruise there. What you're looking at is rainfall with wind stress vectors. The ship was around here during this time. There are two averages. One on the left is during the first part of the cruise. The one on the right is during the second part of the cruise. This is all from the ERA interim analysis. What you see is, indeed, in the first part of the cruise, it was very active. There's quite a bit of rainfall. The most conspicuous difference between these two is the intense rainfall in the northern part of the bay. The other thing is that when you go into the second part, not only does the rainfall diminish, but the wind goes more zonal. I'm not sure why that is, but I found that interesting. So what we wanted to do then was look at, since things are propagating northward, we wanted to look at it in a way where we could clearly see that things were propagating northward. So we took a zonal average between 87 and 92 degrees east, and we plotted it in time. So you can see latitude on the left side here and time on the right. There are two vertical lines here. Those just sort of denote the time period that we felt the monsoon was best represented. It goes from April to November. This is all again in 2018. We actually overlaid some ship data just so you get an idea when the ship was out there, whether or not the reanalysis shows you something that is mostly appropriate or not. What you can see is in the SST plot up here, it's really, really warm, and then when the monsoon comes in, there's this nice northward sort of cooling that occurs quite rapidly. And coinciding with this is a nice little rain band that goes north. So that's the northward propagation of the onset of the monsoon. Of course, there's other things which are quite similar to this that occur later in the year with oscillations. There's sort of this cooling and warming again in the north, which is something we saw, which was very interesting. We don't know quite why, but the northern bay seems to warm up in a cycle that's not as prominent or even absent in the southern bay. Okay, so I'm going to hand off.
Okay, I'm going to talk about the atmospheric forcing during the summer cruise, June summer cruise 2018. These are the various metocean parameters from onboard sensors. And first panel shows the wind speed, and it is like gradually the observation period is from 4th June to 20 June, and we have active and break monsoon, active and break seasons of monsoon during this period. And wind was like actually picking up from like 4 meters per second to 12 up to 4 meters per second to 16 meters per second. And since it is capturing the active and break of monsoon, we could get to compare both scenarios and like how the heat fluxes are responding to that. So the like major heat loss term during the major loss term, heat flux loss term is like latent heat flux. Latent heat flux is the major loss term during the period. Like its value is around like minus 300 watts per meter square. During the active phase of the monsoon, we are having a reduction in net shortwave radiation, and corresponding to precipitation, we can see anomalous drop in air temperature that is due to the convective downdraft of cold air. And as we can expect during the active phase of monsoon, there was a lot of cloud patch and net shortwave radiation is reducing. And since that's because why SST is reducing from the, and from 12 onwards, we are having a break of monsoon, but still SST is reducing. Might be due to the, because even if there is a break, wind speed is not lowering. So that might be the reason for the continuation of the reduction of SST. And late and sensible heat flux is showing some positive value during this period. This is the peculiarity of Bay of Bengal, but this is not important in this context, so I'm not telling about that. And this was the temperature salinity section from the first CTD of ship. So it is like the bay was very warm and warm and fresh during the beginning of the cruise, and we could see some sort of thermal inversion here, and we got a clear very it was like very much stratified during the beginning, and it started mixing up because of the precipitation, and we saw some sort of shoaling of MLD because of this fresh water from precipitations. These are the observations. Thank you.
So we took these atmospheric and surface forcing, and we ran the PWP 1D models of the mixed layers to see if the observations match the model. So this is the fast CTD data, and we saw that the model is in the blue and observed data is in the red. So we saw that the model moderately predicts like overall where the mixed layer depth is in the observation. But in the SST we couldn't predict as observed. We took this PWP model and we ran a few experiments with it to see how the model responds to certain parameter changes. So in the first plot, you see the normal wind stress and the normal the forcing, and we see the mixed layer depth. So this is the period where the wind stress is the most, is the largest, as we saw in the atmospheric forcing here, when 10 to 13. Yeah. So this is when the mixed layer depth deepens the most, and then it continues to stay the same even after the winds have gone. So we reduced the wind to the 10% of the value, and we saw that the mixed layer shallows, and we see the oscillations of the diurnal heating predominantly in the later part, and we also see that there is a layer of a little warmer water because the mixed layer is not mixing too much into the deep. So this is what we saw in the model.
Yeah. So to continue with the to characterize mixed layer depth, like we took the data from one mooring location, BD09, that's in the Northern Bay. Here you see 5 panels. The top panel showing the wind stress vector, and the second one showing how it's changing with time. The period of observation is from early June to mid-July. We see that it picks up around June 10th or June 8th, maybe more precisely. We observe a deepening of the mixed layer shown by the black lines in panel 3 and 4. The third panel shows the salinity and the density, and it shows it clearly starts showing how well the regions get mixed. In the last panel, we try to using the current data. We try to evaluate to see if we can identify near inertial motions, and we were able to find that there exists something resembling near inertial motion, and that seems to follow the wind stress. Now that we were able to identify this near inertial motion, like we tried to see if we can model it, and we proceeded to use the Millet and Pollard model, and we wanted to see like how long it takes for this oscillation to decay or to attenuate. The inputs that go into the model are the Coriolis frequency and the wind stresses, and we use 3 different sources for the wind stress inputs. However, we had to parameterize the decay using this quantity RD, and we find that we try by a method of trial and error. We find that like RD of the order of 1 day inverse is what gave us something like a reasonable agreement with the decay of the oscillations and with regard to the prime. Using a different model, like we find that like this is an idealized model for a two-layer situation, and like we find that the period is not too far off. So with this, I'll give to Aditya.
So I worked in a group which looked at the satellite data products. So here you see the sea surface temperature and sea surface salinity averaged over 3 boxes that we divided the bay into: the northern, the southwest, and the southeast, and as well as the whole bay. So you see the time series here, and you find that in the sea surface temperature, there is this broad overall variability across the seasons. This is across from April to the end of the monsoon period. And you find that the sea surface temperature starts dropping with the picking up of the southwest monsoon winds, and you find that there is small differences between the southeast. You find that there is higher variability in the southeast and the northern part of the bay, close to the river delta regions. And in the sea surface salinity, you see this strong difference between the northern part of the bay and the rest of the bay. You find that there are some oscillations here towards the end of the monsoon period, which is probably from the seasonal oscillations in rainfall over the landmass, which finally you pick up in the sea surface salinity signal. And
all right. So the third sort of theme that we saw, we had a couple groups actually get very excited about some of the response to cyclones that the Bay of Bengal has. So, for example, in the mooring data, we had a very nice story looking at how these eddies propagating through sort of affected lifting up and down the 26-degree isotherm. But when we zoomed into the fall, we were a little confused about a couple periods. For example, here and here, when we had, for example, a sea surface high, but we seem to have a lifting of the isotherm. Of course, this is happening much more rapidly than the satellite can process, but so we're a bit confused about that. So we compared a couple things here on this plot. We have the Q net for heat flux. We have the wind stress modulus and salinity and temperature of the mooring. We also calculated the tropical cyclone heat potential here, and then we have a VISO absolute dynamic topography on the bottom to sort of compare. So the 2 cyclones that happened were a moderate one, Dei, and then a severe one, Title. And you can see that there's this really quite a very apparent mixing and sort of lifting that's happening of the isotherm around Dei. We lost a bunch of the data around here, but possibly this lifting of the isotherm could be explained by the sea surface height.
So here again, we see the time series in the sea surface temperature and salinity, and you see the wind magnitude plotted here. You find that there is the broad seasonal trend in sea surface temperature is to increase, but then when these two episodes occur, you find that the sea surface temperature drops off due to enhanced mixing driven by the higher magnitude of the wind speed. And in the sea surface salinity too, you see this response here. So I'll hand it back to Justin.
All right. So another sort of satellite image of these two cyclones. So during day E, there was a really nice geostrophic anticyclonic eddy that happened right on top of our mooring. This is also very close to where the cyclone started. So if we have our white arrows are the surface velocity currents, and black arrows are wind speeds, you can see that there are sort of opposing forces on each other, which would increase wind stress. But for Titlaid, that didn't line up quite so well. We don't really have an eddy on top of the mooring anymore, and the cyclone has started further south. So to sort of sum up this little story, we did a back of the envelope calculation. We calculated what the wind stress curl was just looking at the wind vectors, and then the relative wind stress curl subtracting the current velocities too. And so red is just the Ekman pumping from the wind speeds, and the blue was with the winds and the currents. And it's much stronger during the first cyclone, even though it was more moderate, the Ekman pumping was stronger. And when we looked at how much the 26-degree isotherm lifted during that period, it was about 4 meters, which is very close to what we saw with our Ekman pumping calculation. And that's it. This was a great experience for everyone.
Questions? Eric.
I guess one thing I'm wondering about from the first half is how the large-scale products compare to the in situ products in terms of the SST they produced and other fields.
What did you put on that? Did you put any of our? Sorry, we're trying to see if we might have something that. I don't think we have it. 1 second. No, it's fine. Okay. So we don't have it to show you, but we do have plots of what? Okay. So we have that one. But what I meant was we actually had some plots where we showed the reanalysis and the ship data on top of it, sort of a line plot type thing. And the difference is that the ship sees much higher wind stress. Right. Did you have the SST he was talking about? Okay, but this is PWP, right? So this isn't what you were asking about. No. Okay.
Any more questions? If not, let's thank our group presenters once more.